Alright, let's continue. Let me open the table of content first. Okay, we are finally on the second piece here, the concurrency. Let's take a look at chapter 25. Concurrency. Okay, a dialogue on concurrency. And thus we reach the second of our three pillars of operating system, concurrency. I thought there were 4 pillars. Nope, that was in an older version of the book. Oh, okay. So, what is concurrency? Oh, wonderful, Professor. Okay. Well, imagine we have a page. Interrupting. Pages again? What is it with you and pages? Yeah. Ever read T.S. Eliot, The Love Song of G. Alfred Prufrock? No, never. Do I dare to eat a peach? And all that fun stuff? Oh yes, oh okay. Apparently the student ever read this T.S. Eliot. I don't know what this is about. Okay. Oh yes, in English class in high school. Great stuff. I really like the part where interrupting again. This has nothing to do with that, okay. I just like peaches. Okay. Anyhow, imagine there are a lot of peaches on a table and a lot of people who wish to eat them. Let's say we did it this way. Each eater first identifies a peach visually and then tries to grab it and eat it. What is wrong with this approach? There are a lot of peaches on the table and a lot of people who wish to eat them. Okay, let's say we did it this way. Each eater first identifies a peach visually and then tries to grab it and eat it. What is wrong with this approach? Okay. Seems like you might see a peach that somebody else also sees. If they get there first, when you reach out, no peach for you. Okay. If they get there first, and when we reach out, no peach for us. Okay. Because the other personality get the peach first. Exactly. So what should we do about it? Well, probably develop a better ways of going about this. Maybe form a line, and when you get to the front, grab a peach and get on with it. Good, but what's wrong with your approach? Sis, do I have to do all the work? Yes. Okay, let me think. Well, we used to have many people grabbing for peaches all at once, which is faster. Well, we used to have many people grabbing for pitches all at once, which is faster. But in my way, we just go one at a time. It is correct, but quite a bit slower, right? The best kind of approach would be fast and correct, probably. Okay, you are really starting to impress. In fact, you just taught us everything we need to know about concurrency. Well done. I did? I thought we were just talking about pitches. Remember, this is usually the part where you make it about computers again. Indeed. My apologies. One must never forget the concrete. Well, as it turns out, there are certain types of program that we call multi-thread application. Never forget the concrete. There are certain types of program that we call multi-thread application. Each thread is kind of like an independent agent running around in this program, doing things on the program's behalf. Okay. But this thread access memory, and for them, each spot of memory is kind of like one of those bits. If we don't coordinate access to memory between threads, the program won't work as expected. Makes sense? Okay. Doing things on the program behalf. Access memory. And for them, each spot of memory is kind of like one of those pitches. Okay. If we don't coordinate access to memory between threads, the program won't work as expected. Makes sense? Kind of. But why do we talk about this in an operating system class? Isn't that just application programming? Good question. A few reasons actually. First, the operating system must support multi-thread application with primitives such as logs and condition variable, which we'll talk about soon. Second, the operating system itself was the first concurrent program. Okay. It must access its own memory very carefully, or many strange and terrible things will happen. Really, it can get quite grisly. Okay, I see. Sounds interesting. There are more details, I imagine. Indeed, there are. Okay. Let me check this chapter 26. An introduction. Concurrency and thread. Wait a minute. Okay, why use thread? Yeah, I'm checking the section here. Thread creation. Why it get worse, set data, the heart of the problem, uncontrolled scheduling, the wish for atomicity. Okay, one more problem waiting for another. Okay. Oh, there is logs, log base. Okay. Now let's take a look at the introduction first. Concurrency and Introduction, Chapter 26. Thus far, we have seen the development of the basic abstraction that the operating system performs. We have seen how to take a single physical CPU and turn it into multiple virtual CPUs, thus enabling the illusion of multiple programs running at the same time. We have seen how to take a single physical CPU and turn it into multiple virtual CPU, right, on the earlier chapter. Okay, thus enabling the illusion of multiple programs running at the same time. We have also seen how to create the illusion of a large private virtual memory for each process. This abstraction of the address space enables each program to behave as if it has its own memory when indeed the operating system is secretly multiplexing address space across physical space, across physical memory, and sometimes this, the swapping mechanism. In this chapter, we introduce a new abstraction for a single running process, that of a thread. A new abstraction for a single running process, that of a thread. Instead of our classic view of a single point of execution within program, that is a single PC where instructions are being fetched from and execute. What PC in here means? Is it personal computer? Maybe. I mean, sometimes we call, what is it called? Program counter as PC too. So yeah, I'm not sure. Maybe this is personal computer. In our classic view of a single point of execution within a program, a single personal computer where instructions are being fetched from and execute. A multi-thread program has more than one point of execution. Okay. Wait. I don't think PC in here stand for personal computer. Program counter, right? Okay. Alright. Program counter, see. Not a personal computer, okay. So a single program counter where instructions are being fetched from and execute. A multi-thread program has more than one point of execution, multiple program counters, each of which is being fetched and execute from. Perhaps another way to think of this is that each thread is very much like a spirit process, except for one difference. They share the same address space and thus can access the same data. Okay. Each thread is very much like a spirit process, except for one difference. They share the same address space and thus can access the same data. Okay. The state of a single thread is thus very similar to that of a process, it has a program counter, the PC, right, that tracks where the program is fetching instruction from. Each thread has its own private set of register it uses for computation. Each thread has its own private set of register it uses for computation. Okay, has its own private set of register it uses for computation. Thus, if there are two threads that are running on a single processor, when switching from running one, let's say T1, to running the other T2, thread 2, something like that, a context switch must take place. Okay. The context switch between threads is quite similar to the context switch between processes, as the register state of T1 must be saved and the register state of T2 restored before running T1. Okay, so context switch is not only from the user program or user application to the, or maybe user mode, I guess. Not only from the user mode to kernel mode in the previous chapter. I forgot which chapter it is. Probably around scheduling. Yeah, maybe the introduction. I don't really remember the specific chapter, but in the previous chapter we are talking about context switch. When switching from the user mode, when we are running the user application, and then we switch to the kernel mode when we are calling the system call, something like that. Okay, so maybe the key point in here to identify whether that is a context switch or not is, do we need to save the register state of the process, maybe something like that? Maybe. So if we need to save the register state, maybe we can call that context switch. But then, is calling a function also considered to be context switch? Yeah, I'm not sure. But for now, maybe we can think of context switch something like, what is it called? We need to save the register state, the current process or thread register state, and then restore the, what is it called? The next process or thread, something like that. With process, we save state to a process control block, PCB, process control block. Okay. Now we will need one or more thread control block. Oh. So there is process control block, or called PCB, and also thread control blocks, TCB. Okay, to store the state of each thread of a process, thread control blocks. Okay, that is one major difference, though in the context switch we perform between threads as compared to process. Okay, one major difference here. The address space remains the same. Oh, okay. There is no need to switch which page table we are using. Switch which page table we are using. Okay. One other major difference between thread and process concerns the stack. In our simple model of the address space of a classic process, which we can now call a single thread process, there is a single stack, usually residing at the bottom of the address space. If you go 26.1 left, guess this one, right? We will take a look at that later. Let me read this first. However, in a multi-thread process, each thread runs independently and of course may call into various routines to do whatever work it is doing. Each thread runs independently and of course may call into various routines to do whatever work it is doing. Run independently, okay. Into various routines to do whatever work it is doing, right? Instead of a single stack in the address space, there will be one per thread. Wait a minute, does that mean the address space, what is it called? Split into multiple stack too? So we have one address space and then multiple stack in those one address space. Is it something like that? There will be one per thread. Let's say we have a multi-thread process that has two threads, okay, in it. The resulting address space looks different. Oh, figure 26.1, right? Okay, we will take a look at that after this. In this figure, you can see two stacks spread throughout the address space of the process. Okay, so the thread stack is in one shared address space. Okay, thus any stack allocated variables, parameters, return values, and other things that we put on the stack will be placed in what is sometimes called thread local storage. Any stack allocate variable, parameters, return value, and other things that we put on the stack will be placed in what is sometimes called thread local storage. We put on the stack will be placed in what is sometimes called thread local storage. That is the stack of the relevant thread. Okay, you may also notice how this ruins our beautiful address space layout, right? Before, the stack and heap could grow independently and trouble only arose when you run out of room in the address space. Here we no longer have such a nice situation. Fortunately, this is usually okay, as stacks do not generally have to be very large, the exception being in programs that make heavy use of recursion. Okay, let me take a look at this figure. 26.1 single thread and multi-thread address space, the code segment where instruction live. Okay, this one. I think this is the single thread application. Let me check. Yeah, single thread process. A single stack usually residing at the bottom of the address space, right? Okay. The heap segment contains dynamic allocation data or malloc data. Dynamic data structure, it grows positively, and then the stack segment contains local variable argument to routines or function, return values, etc. It grows negatively. Okay, in case anyone confused, because I've seen some what is it called? Some material illustrate the stack going downward, right? Rather than upward like this one. It is basically depends on where the lowest address is. So as far as I understand, the stack grow toward the lowest address. So whether it grow, what is it called? Whether the illustration like this one going upward or downward depends on where the lowest address space is. In case anyone confused about the illustration. Sometimes I also find the illustration rather than up or down, they use right with right or left, which is even more confusing. So yeah, the point is that the stack grow towards the lowest address, and that lower address can be at the top or at the bottom or on the right or on the left. So it depends where the lowest address is. So something to keep in mind. Figure 26.1, right? Program code, the instruction, okay, heap, this dynamic allocation. Okay, this is stack 2, this is stack 1. Oh, is it always the case to have the free space between multi-thread stack? I'm not sure. Maybe it is. Okay, why use thread? Before getting into the details of threads and some of the problems you might have in writing multi-thread programs, let's first answer a more simple question. Why should you use thread at all? As it turns out, there are at least two major reasons you should use thread. The first is simple parallelism. Two major reasons. Okay. Parallelism. Imagine you are writing a program that performs operation on very large array. For example, adding two large arrays together, or incrementing the value of each element in the array by some amount. If you are running on just a single processor, the task is straightforward. Just perform each operation and be done. On just a single processor, the The task is straightforward, just perform its operation and done. However, if you are executing the program on a system with multiple processors, you have the potential of speeding up this process considerably by using the processor to each perform a portion of the work. The task of transforming your standard single-thread program into a program that does this sort of work on multiple CPU is called parallelization. Your standard single-thread program into a program that does this sort of work on multiple CPU is called parallelization, and using a thread per CPU to do this work is a natural and typical way to make program run faster on modern hardware. Okay. The processor to each perform a portion of the work. Alright, the second reason is a bit more subtle. To avoid blocking program progress due to slow input-output, imagine that you are writing a program that performs different type of input-output, either waiting to send or receive a message for an explicit this input-output to complete, or even implicitly for a page fault to finish. Instead of waiting, your program may wish to do something else, including utilizing the CPU to perform computation or even issuing further input-output requests. Instead of waiting, your program may wish to do something else, including utilizing the CPU to perform computation or even issuing further input-output requests. Using thread is a natural way to avoid getting stuck. While one thread in your program waits, that is, block waiting for input-output, the CPU scheduler can switch to other threads which are ready to run and do something useful. Threading enables overlap of input-output with other activities within a single program, much like multi-programming did for process across programs. As a result, many modern server-based applications, web server, database management system, and the like make use of thread in their implementation. Of course, in either of the cases mentioned above, you could use multiple processes instead of thread. However, threads share an address space and thus make it easy to share data, and hence are a natural choice when constructing this type of program. Processes are a more sound choice for logical spirit tasks where little sharing of data structure in memory is needed. Okay, let me drink some water first. Yeah, I've been talking so much. My throat is dry. Okay. An example, thread creation. Let's get into some of the details. Say we want to run a program that creates the thread, each of which does some independent work, in this case printing A or B. Say we want to run a program that creates two threads, each of which does some independent work, in this case printing A or B. The code is shown in figure 26.2, page 4. After this, I assume the main program creates two threads, each of which will run the function myThread, though with different arguments, the string A or B. Once a thread is created, it may start running right away, depending on the whims of the scheduler. Alternatively, it may be put on ready but not running state, and does not run yet. Oh, okay. So the thread can start running right away or put it on hold, I guess. Basically not running state, and does not run yet. Okay, of course, on a multiprocessor, the thread could even be running at the same time, but let's not worry about this possibility quite yet. On a multiprocessor, the thread could even be running at the same time, but let's not worry about this possibility quite yet. Okay, running at the same time. So I think there are three, what is it called? Three possibility, maybe something like that. The first thread running first, and then the second thread running after that, and then also the first thread running first, and the second thread is not running yet, and then maybe the third one running, the first and second thread running at the same time. Maybe something like that. Or well, let me take notes, I guess. The possibilities of running thread, I guess. Running, yeah. The first one is that one running first, and then that two running after thread one, or thread one and thread two running at the same time. And then this one have two possibilities too. Thread two running immediately, or thread two put on hold until until when? Until it take rate, maybe something like that. So maybe this is the scenario. That one running first, and then thread 2 running after that one, or running at the same time. the first case, we also have second possibility, thread 2 running immediately or put on hold, something like that. The not running state here. Okay. Alright, this is the code. Okay. After creating the two threads, let's call them T1 and T2. The main thread call pthread join. Okay. My thread, alright. Return null. Oh, comment.h. Yeah, we need to check the comment.h too, I guess. Probably because of this, the uppercase P and then thread create. Okay. Main n, which wait for a particular thread to complete. It does so twice, thus ensuring T1 and T2 will run and complete before finally allowing the main thread to run again. When it does, it will print main n and exit. Overall, 3 threads were employed during this run, the main thread, T1 and T2. This reminds me of fork, I guess. Where is it? Yes, this fork. But I guess the difference is that when we are using thread, we are sharing the address space. Well, if we use fork, we create a new process with spared address space, maybe something like that. So there is the difference, I guess. Okay, let us examine the possible execution ordering of this little program. In the execution diagram, figure 26.3, page 5, time increase in the downward direction, and each column show when a different thread, the main one or thread 1 or thread 2 is running. Note, however, that this ordering is not the only possible ordering. In fact, given a sequence of instructions, there are quite a few, depending on which thread the scheduler decides to run at a given point. Okay. This ordering is not the only possible ordering. Okay. In fact, given a sequence of instructions, there are quite a few depending on which thread the scheduler decides to run at a given point. For example, once a thread is created, it may run immediately, which would lead to the execution shown in figure 26.4, page 5. In the downward direction. Okay, and each column shows when a different thread is running. Okay. Once a thread is created, it may run immediately, which would lead to the execution zone in figure 26.4. We also could even see B printed before A. if say the scheduler decide to run thread 2 first, even though thread 1 was created earlier. Okay. There's no reason to assume that a thread that is created first will run first. Okay. We cannot assume that the I guess there is no guarantee that the thread created first will run first. Okay. Figure 26.5, page 6 shows this final execution order with thread 2 getting to start its stuff before thread 1. What is start? Wait a minute. Okay. Start its stuff before thread 1. Oh. I should make people to see one way to think about thread creation is that it is a bit like making a function call. However, instead of first executing the function and then returning to the caller, the system instead creates a new thread of execution for the routine that is being called, and it runs independently of the caller, perhaps before returning from the create, but perhaps much later. What runs next is determined by the operating system scheduler, and although the scheduler likely implements some sensible algorithm, it is hard to know what will run at any given moment in time. As you also might be able to tell from this example, thread make life complicated. It is already hard to tell what will run when. Computers are hard enough to understand without concurrency. Unfortunately, with concurrency, it simply gets worse, much worse. Alright. Okay. Well, I guess let's check out this code on the next session. Yeah, I need to also check what is in the header here. Common.h and common_thread.h. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.